Thank you so much. And let me talk a little bit about what we are working on at Stevens, and especially the quantum campus project that we are putting our efforts on. So what we do actually upon a lot of equations, but I promise you that I'm not going to show a single equation. If I show one, you can cut my tongue off immediately. So first is, what is quantum? So this is actually an odd question because quantum may appear odd, but actually if you really look into it, it's not as odd. So quantum theory is the most accurate and tested towards our understanding of the physical world around us. And for many, many years, we love Newton's laws. But then later on, we find that just from one equation in quantum mechanics, we can derive the Newton's laws. So for one is that Albert Einstein did not believe quantum, and he had this very famous quote that God does not play dice, which may be true in the classical world, but right now, and we have shown again and again that God does play quantum dice. And it is interesting that before we even come to realize the quantum physics, there are a lot of natural processes already utilizing the quantum mechanics. And so for example, the reason why the green leaves are so efficient in producing energy from the sunlight is because there is underlying quantum processes behind to make it very efficient. And we recently realized that why our noses are so sensitive to the very small, tiny trace of chemicals or odors. It's because it is a quantum device. It is not a classical device that we can understand by using classical mechanics. So it is so odd that people raise this phrase of Schrödinger cat. So you can, in the quantum world, so you are allowed to have a pet that can be both live and dead at the same time. And trust me, I tried to explain this to my wife a million times and I failed. So, but on a much smaller scale, people have observed and verified that over and over again. And so there is a phenomenon also called entanglement. So if you create an entanglement between two hearts, so then you send one to the Mars and you send one to Jupiter, and they will still feel each other because this is within the fundamental laws of physics, so which is actually beyond the normal space-time understanding. And so for the application that we are mostly interested in, we also utilize this measurement postulates. Basically, it says that before you make the measurement, everything is inherently uncertain. So measurement is not just a process of you reading the information from an object. Measurement is a part of the state determining process. Depending on how you measure the object, you can have very different results. And in the quantum physics, we have this de-description of any quantum object by using wave functions. So when you perform the measurement on the quantum object, it will randomly collapse to one of the eigenstates of the measurement apparatuses according to the inherent quantum statistics. So we tend to believe that there is something there, regardless of anybody looking at it or not. But this concept does not hold in quantum physics anymore. So those are just some spooky nature of quantum physics. But the real important question is that why do we care, right? For many, many years, we did not quite care, but it's time to care about it. Why? Because increasingly, number of big problems that we either cannot solve or we cannot have cost-effective solutions to the big problems. So it is now widely envisioned that the quantum technology will revolutionize not just one but many sectors of our society. So in sensing, metrology, imaging, computing network, and data analytics, and at Stevens, my lab is working on 5 or 6 those areas, and we create some exciting result, but in the limited time. So I will just very briefly talk with the 2 projects that we have accomplished at Stevens recently. And the first one is the quantum random number generator, where we utilize the fundamental laws of physics, quantum physics, to create random numbers that you can truly trust and that you can manipulate its statistics by changing the quantum properties of the object that you are measuring, and that you can verify it, that which means that you don't have to trust the vendor who sells the device, which is important especially for the military applications. And the other is the quantum communication network. Actually, we are also utilizing the quantum physics to secure our information exchange. And we have built such a prototype over the Stevens campus. Okay, so first, quantum random number generation. We all know that the random numbers are enormously important. Oftentimes, they are the first step for many cyber applications. And there are different ways to create random numbers. For example, typically, so you can use the measurement of the unpredictable events. For example, so the easiest way is that you flip a coin and to say which side it lands on. But the problem is that it's very hard, almost impossible, to make sure that it's not biased. Even you can do your best to make sure that the coin is good. How about yourself? Right. And the other way is that you can create the pseudo-random numbers just by drawing a code in your MATLAB or mathematical or Python programs, but the problem is that those are not real random. So they may appear random over some finite length of the numbers, but if you do this over again over a long distance, you'll find, I start to repeat myself. That will create a huge problem. So the classical approaches, while they are relatively conceivable, but they are those enormously very serious problems that really force us to think what other ways that we can possibly improve on that. On this side is the classical approach, and the counterpart is the quantum approach. So as we said, so the spooky nature of quantum physics laws allow us to derive some inherent statistics that we know that is random. So the randomness is not derived from our partial incomplete information of the event itself. It is that the event is inherently random. So we are utilizing the fact that the God does play dice. And even the God, him or herself, that could not predict the outcome of the dice. Because it's the physics. So by this way, we can make sure that we really get the genuine randomness, and we don't have to trust anybody. So I think the fact that we can get things done without having to trust anyone is a big question mark in our bigger data age. So this is our first AI experiment on the quantum random number generation. Actually here, I don't think I have time to go much through, but here we are utilizing the quantum mechanical randomized photon arrival time in the machine here, and here we measured the random arrival time for photons here using the single photon detection device, and here it shows some property of our random numbers, which we have modulate the photon to have the uniform distribution here. And you can see here that we actually tried to test it using all the available randomness test software that we can find, and they pass those randomness tests all very nicely. And one of the nice features that our device can do is that we can tailor the probability density distribution of the random numbers. So it's not just that we can create uniformly distributed random numbers, but we can basically modulate it to any statistic property that you want. And again, so we find that they pass all the tests. And here we show more examples. My student had fun here, so they just arbitrarily tried those different statistics, and they also work pretty nice. And we took it a step further, and we developed the quantum decision app, and I have it installed on my cell phone. And so if you install the app, so if you click it, it will take you to our lab, to our quantum device, and you can get your quantum random numbers to your cell phone. And I want to point out that in this app, there is also a little button called the Quantum Mega Million. So we created those random numbers for you to play lottery. It is for free, but it is my very humble request to you that in case you win $1 million, please consider donate 1% to our quantum efforts. So the second is that the quantum communication network. So here we utilize the quantum entanglement to create the shared secret keys between distant parties. What we do here is that we create a pair of entangled photons and we send it to the two end users by quantum channel, which could be the free space optics or fiber optics, but it has to be optics. Unfortunately, it does not work for microwave or RF. And so we perform the quantum measurement on each photon received. And here, if you look at the measurement result on each side, they're completely random. But because of the quantum entanglement, so the random results are perfectly correlated. And by utilizing that, you can apply the standard error correction and to create a shared secret keys and use that. You can use those keys as the one-time impact to perform the private communication because the two parties share the perfectly correlated random keys. And we have implemented this over the Stevens campus, and Stevens is much smaller than here. And here you can see here this is actually the Hudson River. So here this is Manhattan, and my lab is right here. I have a very nice view of the Freedom Tower, but I never find time to really look at it, so it's a waste. So we connected 3 buildings at Stevens, and from my lab to the library, we utilized the fiber optic. So what's one nice thing is that we don't need to lay a new piece of fiber, so we can just utilize existing telecom communication infrastructure. So, and here we have also a free space, and so we have a small prototype of quantum network at Stevens, and here we have also developed the entire user interface there as well, and we built a terminal at the Stevens library, and we call it a quantum corner where if you go to Stevens, you can freely play as long as you don't break it. So in order for our technology to be accepted by this community, we have to find a very compact and cost-effective solution. So that's why we are moving towards this quantum chip development. I think let's just quickly flash through. So when talking about a physics lab, so you could imagine that you have a big floating table with thousands, hundreds of optics on it, with every single optics tuned to be in place within micrometer precision. This is indeed the case, and it is still the case for some of my labs at Stevens, but this is what we are moving towards now. So we are developing the state-of-the-art of very fast microelectronics. In fact, here we develop our own electronics that can be as fast as to detect 20 picosecond signal. So that is really fast. In the meanwhile, so we have started to put more and more components on a single chip. So as you can see here, we have already wire bonded our nanophotonic quantum chip here to realize a functional central processing for the quantum signals. And when you have the two, so this is what you get. We have been able to construct a quantum device based on the quantum nanophotonic technology and this highly integrated, very fast, high-speed microelectronics. And this whole box is powered by a single battery. I put a $20 bill here to show the size. It's not the price of it. So it takes $2 million to have this box at this time, but we hope to maybe to bring it down maybe to $200 in 2 or 3 years, so that more and more people can really start to enjoy the power of quantum technology. So with that, I would like to stop, and so this is a part of my team here, and I have to say that I have about 20 PhD students, and only half of them are in physics. We have students from ECE, actually quite a few students from ECE and computer science, and because it takes much beyond physics to be able to build a system that hopefully this community can accept and can appreciate. Thank you.